So we learned about several generalization of the coloring. And one of the things that we have proved is Brooks theorem. So it essentially says that when G, delta of G is at most, say, so if G is not K sub delta plus 1 and maximum degree of at most, this is at most G, maximum degree of G is at most delta, then its chromatic number is at most delta, unless G is odd cycle. So if you write it in different way, of course here we have to say that G is connected. Did I write it in? Okay, sorry. So this is for connected one. So for non-connected one, we can just say if G has no K sub delta plus 1 as a subgraph, so this is correct statement. So Brooks theorem essentially says that as long as G does not contain a large clique, maximum possible clique, then we can actually have a better bound on the chromatic number. Then it's natural to ask that what if we forbid, even smaller clique? So we have defined this clique number, which is the size of the, order of the largest clique in G. So if we have further restriction on this clique number, can we actually improve this? Which is actually possible. And Brodin and Kostochka in 77, and Kathleen, I think, is 78, prove that if we know that this clique number is R minus 1 and R is at least 4, then we can bound this chromatic number by R minus 1 over R times delta of G plus 1. So when R equals delta plus 1, then this is exactly same as delta of G. So it's Brooks theorem. And for smaller, clique number, we can actually get the improvement. And how do we prove this statement? So in here, Brooks theorem says that if we have some, some graph which doesn't have a small clique, then we can improve this by 1. But what if we have no, say, K sub delta over 2? Then what we can do is we apply the Robas theorem. Robas shows that we can actually partition the graphs into several graphs, so that each of them has not too large maximum degree. So which is essentially same as S sub R coloring. So what we do is we can actually, in this case, we can partition the graph into 2, so that this has maximum degree at most delta over 2 and delta over 2. Then this is maximum degree delta over 2 and then has no case of delta over 2. So Brooks theorem saves 1 here and Brooks' theorem saves 1 here. And then we just combine the coloring. So this can be colored by delta over 2 color, and this can be saved by the, one less color than the maximum degree plus 1 and maximum degree plus 1. So that's the basic idea. So let's write it in rigorous way. Let T be this number, and let Di be R minus 1 for I between 1 and T minus 1, and dt be the remaining number. So we partition this, we partition delta into, not delta. Give me a moment. So what was the Roberts theorem? Roberts theorem was this. When we have numbers which sum up to the maximum degree minus k minus 1, then we can partition it into, each part, so that each part has not so large maximum degree. So we want to partition, we want to find the d1 to dk, which are as even as possible. So, and all of them are smaller than r minus 1, smaller than or equal to r minus 1. So let's say all of them are smaller than r minus 1. And then, depending on the, congruence class where the delta belongs to, when congruent to r, we have the one last thing. So we know that this is at most r minus 1. Then, what do we have? Summation of di is delta of g minus t plus 1. And wait, did I say it incorrectly? Sorry, give me a moment. Oh, yeah, sorry. This last one is at least r minus 1, because delta of g plus 1 is at least rt from here. So delta of g minus rt plus r is at least r minus 1. So this last number is also at least r minus 1. So we put as many r minus 1 as possible, and then so that the last one is also at least r minus 1. So by Roberts' theorem, what we can do, we can partition the vertices of G into B1 to Bt such that each Gi has maximum degree m of Di, where this Gi is the graph, subgraph of G induced by Bi. As G has no R clique, and Di is at least r minus 1, we can apply Brooks' theorem. And we know that R is, this r minus 1 is at least 3. So we can forget about the old cycle. And then this does not, have an R clique, meaning that it is not complete graph. Brooks' theorem yields that chromatic number of each one is m of Di. So we have this V1, V2 to VT, and then we color this, and we color this. While doing that, we use some colors here, then we use totally different color here. So we use the disjoint color set for each, vertex set. So if we use 1 to say DI here, then D1 here, then we use D1 plus 1 to D1 plus D2 here on V2, and then next one. So we color the subgraphs with disjoint color sets. Then what do we get? The chromatic number of G is at most the chromatic number of G1 to GT summed together, which is summation of DI, which is delta plus 1 minus T, which is R minus 1 over R, delta of G plus 1, taking the ceiling. So this shows the upper bound. So here, if you see, then our gain is around this. So from, if we don't know anything, then we have a delta plus 1. But now we can actually lower approximately this much, more on the upper bound. So this is huge gain if R is small. But for large R, this is not so big gain. So it's natural to ask that can you get, what bound can we get for, large R? And by the way, so from this, what we can get is, for example, if we have a triangle free graph, then what does it say? If we have a triangle free graph, then you cannot apply this for R equals 3. So R equals 4. Let's change this into R minus 1, where R minus 1 is at least 3. So this is more correct way of writing this theorem. Then we cannot apply for the result for R equal 3. So we put R equal 4, then this becomes 4 over 3 delta G plus 1. So that's the upper bound for the triangle free graph. But there are actually better bound. In 1996, Johansson proved that if we have a triangle free graph, satisfy that there exists some constant, so that its chromatic number is at most the constant times the maximum degree over log maximum degree. And that's a side note. And then regarding bounding chromatic number in terms of Kling number, there is a famous conjecture by Bruce Reed. Who conjecture that the maximum degree plus the Kling number plus 1 over 2 would bound the chromatic number. This is known for, the case where this chromatic number is roughly very close to the maximum degree for small epsilon. But the general case is still open. So now we move to the section 4.2, which studies other variations of the coloring. We move that there to, we move to there in the next video.